Kepler's laws of planetary motion. A late-night lecture for the weary scholar. Good evening. Tonight we will be covering Kepler's laws of planetary motion. We will proceed slowly, and we will be thorough, and we will leave no detail unexamined, because it is only through careful, patient, and methodical examination of each concept that a true and lasting understanding can be achieved. There's no need to rush. The material will come to us gradually, as it came to Johannes Kepler himself, over the course of many years of painstaking observation and calculation. Part 1. Historical and biographical context. Johannes Kepler was born on the 27th of December in the year 1571 in the town of Weil der Stadt, in the Holy Roman Empire, in what is now the modern nation of Germany. He was born into relatively modest circumstances, and his early life was marked by illness and hardship, the details of which need not concern us greatly this evening, but which are worth noting simply because they remind us that the process of scientific discovery is undertaken by human beings who exist within the full complexity of human circumstances. Kepler studied at the University of Tübingen, where he encountered and became deeply influenced by the heliocentric model of the solar system proposed by Nicolaus Copernicus. Copernicus, who had published his great work, De Revolutionibus Orbium Coelestium, in 1543, had proposed that the planets, including the Earth, revolve around the Sun rather than around the Earth. This was, as many of you are no doubt aware, a profound and consequential departure from the prevailing geocentric model that had dominated European and indeed much of global astronomy for well over 1,000 years, tracing its origins to the works of Aristotle and Ptolemy. Kepler eventually came to work as an assistant to the Danish astronomer Tycho Brahe, who had, over the course of decades, accumulated the most precise and extensive collection of naked-eye astronomical observations in history. Tycho Brahe was himself a fascinating figure, a man of enormous wealth and enormous ego, who had constructed observatories on the island of Fenn, in the strait between Denmark and Sweden, and who had measured the position of stars and planets to an accuracy that would not be surpassed until the invention of the telescope. It is worth dwelling on this for a moment, because the precision of Tycho's observations was absolutely essential to Kepler's later work. Without accurate data, the subtleties of planetary motion that Kepler sought to describe would have been completely invisible. Tycho Brahe died in 1601, and Kepler, who had been working with him in Prague, inherited his observational records. These records, and particularly the detailed observations of the planet Mars, became the raw material from which Kepler would extract his three laws. The planet Mars was particularly important because its orbit deviates more noticeably from a perfect circle than the orbits of, say, Venus or Jupiter, and this deviation was large enough to be detectable even in naked-eye observations, provided those observations were as precise as Tycho's. Kepler published his first two laws in a work called Astronomia Nova, meaning the new astronomy, in the year 1609. His third law appeared a decade later in a work called Harmonicas Mundi, meaning the harmony of the world, published in 1619. The third law was embedded within a much larger and more mystical work in which Kepler attempted to relate the orbital periods of the planets to musical harmonies, a project that most modern scientists would regard as misguided, but which reflects the intellectual and cultural context in which Kepler was working. The important point for our purposes this evening is that the third law is correct, regardless of the philosophical framework in which it was originally presented. Part 2. Preliminary concepts and definitions. Before we proceed to the laws themselves, it will be useful to establish some definitions and preliminary concepts, because a careful understanding of the laws requires a careful understanding of the geometric and physical vocabulary in which they are expressed. The first concept we should establish is that of an ellipse. An ellipse is a closed, planar curve such that the sum of the distances from any point on the curve to two fixed interior points, called the foci, is constant. The foci are the plural of focus, and the singular is focus, and we will use both forms this evening. If we call the two foci f1 and f2, and if we choose any arbitrary point P on the ellipse, then the sum of the distance from P to f1 plus the distance from P to f2 is always the same constant value, regardless of where on the ellipse P is located. This constant value is equal to 2 times a day, where a is called the semi-major axis. The semi-major axis is half the length of the longest diameter of the ellipse, and it is one of the two fundamental size parameters of an ellipse. The other fundamental size parameter is b, called the semi-minor axis, which is half the length of the shortest diameter of the ellipse. The relationship between the semi-major axis, A, the semi-minor axis, B, and the distance from the center of the ellipse to either focus, which we denote by C, is given by the equation a squared equals b squared plus c squared. In other words, a squared is equal to b squared plus c squared, which can be rearranged to give c squared equals a squared minus b squared, or equivalently, b squared equals a squared minus c squared. There's another parameter of an ellipse that will be important to us this evening called the eccentricity, which is typically denoted by the letter E. The eccentricity is defined as E equals C divided by A, or in other words, E is equal to the ratio of the focal distance to the semi-major axis. For a perfect circle, the two foci coincide at the center, so CE equals 0, and therefore E equals 0. For an elongated ellipse, CE approaches A, and therefore E approaches 1. A parabola has an eccentricity of exactly 1, and a hyperbola has an eccentricity greater than 1. The planetary orbits in our solar system are all ellipses, with eccentricities less than 1, and indeed most of them have eccentricities that are quite small, meaning that they are only slightly elongated from perfect circles. Another geometric concept we will need is that of the perihelion and the aphelion. The perihelion is the point in a planetary orbit at which the planet is closest to the Sun. The aphelion is the point in a planetary orbit at which the planet is farthest from the Sun. The word perihelion comes from the Greek words peri, meaning around or near, and helios, meaning sun. The word aphelion comes from the Greek words apo, meaning away from, and helios, again meaning sun. The distance from the Sun to the planet at perihelion, which we call r subscript perihelion, is equal to at times the quantity 1 minus e. The distance from the Sun to the planet at aphelion, which we call r subscript aphelion, is equal to at times the quantity 1 plus e. These two expressions follow directly from the geometry of the ellipse and the definition of the eccentricity, and it is worthwhile to simply hold them in mind as we proceed. Part 3. Kepler's first law. We are now in a position to state Kepler's first law. Kepler's first law states that each planet moves in an elliptical orbit with the Sun located at one of the two foci of the ellipse. Let us restate this in slightly different words. Every planet in the solar system travels along a path that is an ellipse, and the Sun is not at the center of that ellipse, but rather at one of the two special interior points called foci. The other focus is simply an empty point in space, with no physical object located there. Let us restate it once more. The orbit of each planet is an ellipse, not a circle, and the Sun occupies one focus of that ellipse. This was a profound departure from the astronomical tradition that preceded Kepler. From the time of Aristotle through the work of Ptolemy, and even through the early heliocentric work of Copernicus, it had been assumed that planetary orbits were, in some fundamental sense, circular, or were constructed from combinations of circular motions. The circle was regarded as the most perfect geometric form, and it seemed philosophically natural that the motions of the heavenly bodies should reflect this perfection. Kepler's first law was a break with this tradition. Planets do not move in circles, they move in ellipses. The physical derivation of the first law, which Kepler himself did not possess, requires the full machinery of Newtonian mechanics and differential calculus, both of which were developed by Isaac Newton after Kepler's death. Newton showed, in his Principia Mathematica of 1687, that a body subject to an attractive central force that varies as 1 over ER squared, where AR is the distance from the attracting center, must follow a conic section, and that conic section is an ellipse for bound orbits, a parabola for an orbit with exactly enough energy to escape, and a hyperbola for unbound orbits with more than escape energy. The force in question is, of course, gravitational attraction, and Newton's law of universal gravitation tells us that the magnitude of the gravitational force between two bodies of masses, m and m, separated by a distance e cr, is equal to g times m divided by r squared, where g is the universal gravitational constant. The formal derivation proceeds by writing Newton's second law for the planet of mass m acted upon by the gravitational force from the sun of mass m. Newton's second law in vector form says that the force vector equals m times the acceleration vector. The gravitational force vector points toward the sun and has magnitude g times m divided by r squared. Working in polar coordinates r and theta, one arrives at 2 coupled second-order ordinary differential equations for r as a function of time and theta as a function of time, by making the substitution u equals 1 divided by r, and by using conservation of angular momentum, one can reduce this system to a single second-order linear ordinary differential equation for u as a function of theta. This equation has the general solution u equals 1 divided by r equals, in its orbit equation form, the expression 1 plus e times the cosine of theta, all divided by the parameter p, where p is the semi-latus rectum, defined as b squared divided by a, or equivalently as a times the quantity 1 minus e squared. This is the polar equation of a conic section with the origin at one focus, and for values of e between 0 and 1 exclusive, it describes an ellipse. This confirms Kepler's first law from first principles. Part 4. Kepler's second law. Kepler's second law states that a line segment joining a planet to the sun sweeps out equal areas in equal times. Let us rephrase this. If we draw an imaginary line from the sun to a planet, that line sweeps across a region of space as the planet moves. Kepler's second law says that no matter where in the orbit the planet is, the area swept out by this line in any given interval of time is always the same. Whether the planet is near the sun or far from the sun, whether it is at perihelion or aphelion or anywhere in between, the rate at which area is swept out is constant. To say it yet another way, the areal velocity of the planet, meaning the area swept per unit time, is constant throughout the orbit. One immediate and important consequence of this law is that planets move faster when they are closer to the sun, and slower when they are farther from the sun. Near perihelion, where the line from sun to planet is short, the planet must be moving quickly along its orbit in order to sweep out the same area per unit time as it does near aphelion, where the line from sun to planet is long. This is somewhat counterintuitive if one thinks of orbits as being like cars on a track traveling at constant speed, but it is nonetheless exactly what is observed. The physical basis of Kepler's second law is conservation of angular momentum. This is one of those beautiful connections in physics where a geometric law about areas turns out to be the direct expression of a fundamental conservation principle. Let us trace through the reasoning. The angular momentum, L, of the planet about the sun is defined as the cross product of the position vector r with the linear momentum vector p equals m times v, where v is the velocity vector. For a body moving in a plane, the magnitude of the angular momentum is L equals m times r times v subscript perpendicular, where v subscript perpendicular is the component of the velocity perpendicular to the position vector. Now, the rate at which area is swept out by the line from the sun to the planet can be calculated as follows. In a small time, interval delta t, the planet moves a small distance along its orbit. The small triangle formed by the position vector at the beginning of the interval, the position vector at the end of the interval, and the arc of the orbit has an area that is approximately equal to 1/2 times AR times the distance moved perpendicular to R, which is R times V subscript perpendicular times delta TT. So the area of the small triangle is approximately 1/2 times R times V subscript perpendicular times delta T. Therefore, the rate of change of area with respect to time, which we write as dA divided by dt, is equal to 1/2 times R times V subscript perpendicular, which equals L divided by 2m. Since gravitational force is a central force, meaning it always points directly toward or away from the Sun with no tangential component, there is no torque acting on the planet about the Sun, and therefore the angular momentum L is conserved, meaning it does not change with time. Therefore, dA divided by d2 is constant, which is precisely Kepler's second law. This derivation tells us something important, namely that Kepler's second law is not special to gravity or to the inverse square law. It applies to any body moving under the influence of any central force, as long as the force has no component perpendicular to the line connecting the body to the attracting center. Kepler's first and third laws, on the other hand, are specific to the inverse square nature of gravity. Physicist, Part 5. Kepler's third law. Kepler's third law states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. We can express this mathematically by saying t squared is proportional to a cubed, or, to include the constant of proportionality, t squared equals 4 pi squared divided by the quantity g times m, all multiplied by a cubed. In this expression, t is the orbital period, a is the semi-major axis, g is the universal gravitational constant, and m is the mass of the Sun. Let us restate this. The time it takes a planet to complete one full orbit around the Sun, when squared, is proportional to the cube of the average distance of that planet from the Sun. If planet A has a semi-major axis that is 4 times as large as planet B's, then planet A's orbital period will be 8 times as long as planet B's, because 4 cubed is 64 and 8 squared is 64, and so the ratio of the squares of the periods equals the ratio of the cubes of the semi-major axis. Restating once more in still different words, the quantity t squared divided by a cubed is the same constant for all planets orbiting the same central body. The derivation of Kepler's third law from Newtonian mechanics is most simply performed for the special case of a circular orbit, and the result for elliptical orbits differs only in the sense that the radius r of the circular orbit is replaced by the semi-major axis of the elliptical orbit. Let us proceed with the circular case. For a planet of mass m in a circular orbit of radius r around the Sun of mass m, the gravitational force provides the centripetal force necessary to maintain circular motion. The gravitational force has magnitude g times m divided by r squared. The centripetal force required for circular motion has magnitude m times v squared divided by r, where v is the orbital speed, or equivalently m times 4 pi squared times a divided by t squared, where t is the orbital period, since the speed v in terms of the period is v equals 2 pi times r divided by t, setting the gravitational force equal to the required centripetal force. We have g times m divided by r squared equals m times 4 pi squared times r divided by t squared. The mass em of the planet cancels from both sides, which is a physically important result in its own right because it means the orbital period does not depend on the mass of the planet. We are left with g times m divided by r squared equals 4 pi squared times r divided by t squared. Rearranging this equation, we multiply both sides by r squared and by t squared, and divide both sides by g times m, and so obtaining t squared equals 4 pi squared times r cubed divided by the quantity g times m. This is Kepler's third law. The square of the period t squared is equal to 4 pi squared divided by gm multiplied by r cubed. For the more general elliptical case, r is replaced by a, the semi-major axis, giving t squared equals 4 pi squared divided by gm, all times a cubed. Note that the combination 4 pi squared divided by gm is a constant that depends only on the mass m of the central body. All planets orbiting the Sun share the same value of this constant. If one were instead to consider the moons orbiting Jupiter, one would find a different constant, 4 pi squared divided by g times m subscript Jupiter, but all moons of Jupiter would share that same new constant value among themselves. This is why Kepler's third law, while it was originally stated as a proportionality, needs the full Newtonian formula to connect it to the actual physical properties of the system. Part 6. Physical interpretation and deeper understanding. Let us now spend some time on the physical interpretation of these three laws, because understanding what the laws mean physically is at least as important as knowing how to state them or derive them. Kepler's first law tells us about the shape of orbits. Planets do not wander in straight lines through space, nor do they spiral inward or outward, nor do they travel in perfect circles. They follow closed elliptical paths, and they follow these paths repeatedly, tracing the same ellipse again and again with each orbit. The Sun, which is the gravitating center, is offset from the center of the ellipse and sits at one of the foci. The other focus is a geometric point with no special physical significance, though it appears naturally in the mathematical description. For Earth, the eccentricity of the orbit is approximately 0.0167, which means the orbit is very nearly circular, but not exactly circular. The semi-major axis of Earth's orbit is approximately 1.496 times 10 to the 11th meters, which is defined as 1 astronomical unit, or 1 AU. The perihelion distance is approximately 1.471 times 10 to the 11th meters, and the aphelion distance is approximately 1.521 times 10 to the 11th meters. These differ by about 3%. Kepler's second law tells us about the speed of a planet as it moves through its orbit. The planet speeds up as it approaches perihelion and slows down as it recedes toward aphelion. For Earth, this means that Earth moves slightly faster in January when it is near perihelion than in July when it is near aphelion. The variation in speed is relatively small for Earth's nearly circular orbit, on the order of a few percent. But for a highly eccentric orbit like that of a comet, the variation can be enormous. A comet near perihelion may be moving at tens of kilometers per second, while the same comet near aphelion may be moving at only a fraction of a kilometer per second. The second law also has practical consequences for timekeeping. Because Earth moves faster in some parts of its orbit than others, the Sun does not appear to move across the sky at a perfectly uniform rate over the course of the year. This leads to the phenomenon known as the equation of time, which is the discrepancy between solar time as defined by the actual position of the Sun and mean solar time as used in our clocks. The equation of time can amount to as much as about 16 minutes of discrepancy in either direction over the course of a year. Kepler's third law tells us about the relationship between size and time in orbital dynamics. Larger orbits take longer to complete. This is intuitively reasonable. A planet in a larger orbit has a longer path to travel, and it also moves more slowly because the gravitational pull of the Sun is weaker at greater distances. These two effects combine to make the period grow as the 3/2 power of the semi-major axis. To be explicit, since t squared is proportional to a cubed, we can take the square root of both sides to get t proportional to a 2 to the power of 3/2. If one increases the semi-major axis by a factor of 8, the period increases by a factor of 8 to the 3/2 power, which is 8 times the square root of 8, which is 8 times 2.828, which is approximately 22.6. And if one increases the semi-major axis by a factor of 100, the period increases by a factor of 1000. Part 7. Applications and extensions. Kepler's laws and their Newtonian derivations have enormous practical importance in astronomy and space science, and it is worth discussing some of these applications in a measured and thorough way. The first major application is the determination of planetary masses. From Kepler's third law, specifically the expression t squared equals 4 pi squared divided by gm times a cubed, one can solve for m to get m equals 4 pi squared times a cubed divided by the quantity g times t squared. If we know the orbital period t of a moon or other satellite around a planet, and we know the semi-major axis a of that satellite's orbit, we can calculate the mass m of the planet. This technique was used to determine the masses of all the outer planets of the solar system before spacecraft were sent to visit them. For instance, Jupiter's mass can be calculated from the orbital periods and semi-major axes of its 4 large Galilean moons, Io, Europa, Ganymede, and Callisto. Each moon independently gives a consistent estimate of Jupiter's mass, which is reassuring evidence that the theory is correct. The second major application is the calculation of spacecraft trajectories in space travel. When a spacecraft is sent from Earth to Mars, for example, the most energy-efficient path is not a straight line, but rather an elliptical arc whose perihelion is at Earth's orbit and whose aphelion is at Mars's orbit. This path is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it in 1925. The time required to complete this half-ellipse, known as the transfer time, can be calculated directly from Kepler's third law. Specifically, the semi-major axis of the transfer orbit is the average of the semi-major axis of Earth's orbit and Mars's orbit. And Kepler's third law gives us the full period of that ellipse, so the transfer time is half of that period. The third major application is the discovery of exoplanets, meaning planets orbiting stars other than the Sun. One method of exoplanet detection, called the radial velocity method or Doppler spectroscopy method, detects the small wobble that a planet induces in its host star's motion. The period of this wobble is the same as the orbital period of the planet, and once the period t is known, Kepler's third law can be used to infer the semi-major axis a of the orbit, provided the mass of the star is known. Another method, the transit method, detects the slight dimming of a star's light when a planet passes in front of it, and again the period between transits gives the orbital period, which via Kepler's third law yields the orbital semi-major axis. The fourth application worth mentioning is binary star systems, in which two stars orbit their common center of mass. Kepler's third law, in its general form for a two-body problem, states that t squared equals 4 pi squared divided by g times the quantity m1 plus m2, all times a cubed, where a is now the semi-major axis of the relative orbit, meaning the orbit of one star as seen from the other. By measuring both t and a for a visual binary system, astronomers can determine the total mass m1 plus m2 of the system. If additional information is available, such as the ratio of the distances of the two stars from the center of mass, the individual masses can be disentangled. Part 8. The role of Newton. No lecture on Kepler's laws would be complete without a careful discussion of Newton's contributions, because it was Newton who transformed Kepler's empirical descriptions of planetary motion into a deductive system derived from universal physical principles. Kepler arrived at his three laws through a painstaking process of fitting mathematical models to observational data. He did not know why planets moved in ellipses. He did not have a theoretical framework that predicted this behavior. He simply discovered, through years of computation, that an elliptical orbit with the Sun at one focus provided a much better fit to Tycho's data for Mars than any other model he tried, including the various circle-based models that had been employed by his predecessors. Newton, writing in his Principia Mathematica of 1687, showed that all three of Kepler's laws follow mathematically from two foundational principles: Newton's own three laws of motion and the law of universal gravitation, which states that every two bodies in the universe attract each other with a force equal to g times the product of their masses divided by the square of the distance between them. From these foundations, Newton derived that bound orbits under an inverse square attractive force must be ellipses. He derived that the force directed always toward the Sun automatically implies that equal areas are swept in equal times as a consequence of angular momentum conservation. And he derived the precise form of the third law, including the constant of proportionality 4 pi squared divided by gm. This was one of the greatest intellectual achievements in the history of science. Newton had shown that the motions of the planets, which had been painstakingly mapped by astronomers over millennia, were not the result of divine caprice or mystical harmony, but were the inevitable mechanical consequence of a single universal force operating according to a simple mathematical law. Kepler's laws, which had seemed like brute empirical facts, suddenly had explanations. They were theorems, derivable from more fundamental postulates. It is also worth noting that Newton's approach generalized Kepler's laws in important ways. Newton showed that the orbital shapes are not limited to ellipses, but include all conic sections, with the type determined by the total energy of the system. A bound orbit with negative total energy is an ellipse. An orbit with exactly zero total energy is a parabola. An unbound orbit with positive total energy is a hyperbola. Newton also showed that Kepler's third law applies not just to planets orbiting the Sun, but to any two bodies orbiting under gravity, including moons, binary stars, and artificial satellites. Dacrysuricine, Part 9. Limitations and modern extensions. While Kepler's laws, as derived from Newtonian mechanics, provide an excellent description of planetary motion in most practical situations, they are not the final word, and we should spend a moment noting their limitations and how they are addressed by more modern theories. The most important limitation is that Newtonian gravity is not the ultimate theory of gravitation. Einstein's general theory of relativity, published in 1915, supersedes Newton's theory in all domains and reduces to it in the limit of weak gravitational fields and slow velocities compared to the speed of light. General relativity predicts small but measurable corrections to the orbital motion predicted by Newton's theory. The most famous of these corrections is the precession of the perihelion of Mercury. In Newtonian mechanics, if the Sun were perfectly spherical and there were no other planets, the orbit of Mercury would be a perfect ellipse that repeats exactly, with the perihelion always at the same point in space. In reality, the perihelion of Mercury advances, meaning it slowly rotates around the Sun, completing a full revolution in several 100,000 years. Most of this precession is explained by the gravitational perturbations from the other planets, particularly Venus and Jupiter. However, even after accounting for all planetary perturbations, there remains an unexplained residual precession of approximately 43 arc-seconds per century. This discrepancy baffled astronomers for decades after it was first measured. Einstein's general theory of relativity predicts exactly this amount of additional precession as a consequence of the curvature of space-time near the Sun, and this agreement between prediction and observation was one of the first major confirmations of general relativity. Another limitation of Kepler's laws as standardly derived is that they treat the Sun as fixed and the planet as having negligible mass compared to the Sun. In reality, both the planet and the Sun orbit their common center of mass, and the Sun itself is slightly perturbed by the gravitational pull of the planets. These effects are small for the Earth-Sun system, where the center of mass is well inside the surface of the Sun. But they are more significant for Jupiter, whose mass is large enough to move the center of mass of the Jupiter-Sun system to a point just outside the solar surface. The full two-body treatment, as Newton himself carried out, replaces the mass m of the Sun in Kepler's third law with the sum of the two masses, m subscript Sun plus m subscript planet. But since the planetary masses are generally much smaller than the solar mass, this correction is very small for most purposes. There is also the matter of perturbations. The derivation of Kepler's laws assumes that each planet is acted on only by the Sun's gravity. In reality, every planet is also pulled by the gravity of every other planet, and these perturbations cause the orbits to deviate slightly from perfect ellipses. The actual orbits precess slowly, and the eccentricities and inclinations oscillate over millions of years. These perturbations are the subject of celestial mechanics, the branch of astronomy devoted to studying the long-term behavior of gravitational systems. Modern celestial mechanics can trace the evolution of planetary orbits over billions of years, using numerical integration of the equations of motion on computers. And these simulations show that the solar system is, over very long timescales, mildly chaotic, meaning that small perturbations in the initial conditions of planetary orbits can grow exponentially over time. Part 10. Summary and recapitulation. We have covered a great deal of material this evening, and it is appropriate to end with a systematic recapitulation of the main points, stated clearly and in summary form, so that they may be reviewed and remembered. Kepler's first law states that the orbit of each planet around the Sun is an ellipse, with the Sun located at one of the two foci of that ellipse. This law describes the shape of planetary orbits. It replaced the older tradition of circular orbits. It can be derived from Newton's law of universal gravitation and Newton's laws of motion by solving the differential equations of motion for a body subject to an inverse square attractive central force. Kepler's second law states that the line connecting the Sun to a planet sweeps out equal areas in equal intervals of time. This law describes the variation in a planet's speed as it moves through its orbit, specifically the fact that the planet moves faster near perihelion and slower near aphelion. It is equivalent to the conservation of angular momentum and is a consequence of the central nature of the gravitational force. Kepler's third law states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit, with the constant of proportionality equal to 4p squared divided by the quantity g times m, where m is the mass of the Sun. This law describes the relationship between the size of an orbit and the time required to complete it. It allows astronomers to determine the masses of planets and stars from orbital measurements, and it underlies the design of spacecraft trajectories and the interpretation of exoplanet observations. These three laws, taken together, constitute a complete kinematic description of planetary motion in the idealized two-body problem with an inverse square force. They are among the most significant empirical generalizations in the history of science, representing the fruits of decades of observational work by Tycho Brahe and years of computational analysis by Kepler himself, and they were subsequently explained and unified by Newton within a framework of universal physical law that remains one of the great monuments of scientific thought. The material presented tonight, taken slowly and reviewed carefully, represents the foundation of orbital mechanics and celestial dynamics, and a thorough understanding of it will serve as a firm basis for the study of all further topics in classical and modern astronomy. This concludes tonight's lecture on Kepler's laws of planetary motion. Please review your notes.